Hello, everybody. This is Mr. Tam back with another episode of Science Option 5 for Mathematics. So today what I'd like to explore with you is something we call the trig function of tangent, or the tan function. So what you notice that I've drawn here is part of a unit circle in order to help us graph the tan function. So first, we need to remind ourselves what tan represents. So in a right angle triangle, we know that if this were to represent the unit circle with the radius being 1 here, we know that the y value represents sine, and the cosine value represents the x value. And if we were just to have this as a regular right angle triangle, and this was our angle of interest right here, theta, this side would be considered opposite, and this side would be considered adjacent. Now we remember that tan of theta should be the opposite side divided by the adjacent side. However, in the particular scenario we're dealing with, where we're dealing with a unit circle, opposite is sine, and the adjacent is cosine. And therefore, we could establish that tan is simply sine divided by cosine. Or in this case, what this also represents is a y value, and the bottom here represents an x value. So in reality, it's kind of like what you guys have seen in the past, where it's y divided by x, a little bit like slope, but very far from it. So what does it mean when it comes to our unit circle? Well, let's start with something very simple. Let's start at coordinate 0 right here, this angle 0, where our x and y coordinates are respectively 1 and 0. So if I were to show you the calculation for this, and I wanted to find the tan relationship of that angle theta, I would simply take, again, sine divided by cosine, in this case 0 divided by 1, and that would give me 0. So it's basically saying at an angle of 0, my y value is 0, which means one of the points that I need is the origin. So let's erase this and try another value. So let's try pi over 6. Now pi over 6, as you can see right here, has the coordinates of square root 3 over 2 and 1/2 being the y. So if I again take the whole idea of taking 1/2, which represents my y, and dividing this by square root 3 over 2, what ends up happening is now I have 1/2 multiplied by 2 over root 3. This essentially, let me just write it so it's clear here. This essentially would give me 1 over root 3, which if we rationalize, will give me root 3 over 3. And if I take my calculator and divide square root 3 over 3, that actually gives me 0.577, which is, we're going to estimate to be approximately here. Now, that being said, I'm going to skip pi over 4 for the time being and solve for pi over 3. And there's a reason for that, and it's because I want to save the easiest for last. Now, I'm going to take, instead of half divided by root 3 over 2, I'm going to take root 3 over 2, which represents my angle here at pi over 3. And I'm going to 3 over 2 divided by 1/2, which, if we apply our fraction knowledge properly, is root 3 over 2 times 2 over 1. And the 2's cancel, leaving you with root 3. Now, if I punch in root 3 into my calculator, square root 3 is 1.73, which leads me to approximately this location right here. Now, the nice thing about pi over 4 is that it's an isosceles triangle. And we know something very special about isosceles triangle in that all sides have the same value. Now, since the sides have the same value, what's nice is root 2 over 2, even though we don't know what exactly those numbers are, just turn out to be 1, at which point we take pi over 4 and now label it 1. And I'd like to finish off by now taking pi over 2, which has a y value of 1, and I'm going to divide it by the x value of 0. Well, there's a problem here. Anything divided by 0, as we remember, is not 0, but an infinite solution or no solution at all. So what that means is I've drawn those lines for you as dotted lines. Those are what we call asymptotes. And essentially, as we approach pi over 2, we end up with a line that never actually touches that asymptote. Now, if I were to use the same kind of value, and I'm going to now explore the fourth quadrant of my unit circle, and I look at, let's say, 11 pi over 6. We can equally say that 11 pi over 6 can also be represented by negative pi over 6. And I'd like to do that because when we're dealing with a Cartesian plane, it's easier, of course, to label it as negative pi over 6 if we wanted to show the second half of the cycle. So we're going to now look at this value right here, negative pi over 6 or 11 pi over 6. Both of them mean the same thing. And of course, I'm going to take y divided by x. I'm going to have y, which happens to be negative 1/2 over root 3 over 2, which we've done before. And of course, as you guys have already figured out, this is just root 3 over 3, which is pretty much in the same location as it was pi over 6, but in the quadrant opposite from it. So I'm sorry this has to squeeze a little bit here, guys, but it's approximately here. And if we go and mirror the locations where they are in my quadrant 1, but in quadrant 3, I can start clearly seeing a pattern that this this type of trig function is a weird looking one, actually. And this point right here, the origin where it basically changes the type of shape where it increases, is called the point of inflection. And when we go to modify our tan function later, this is where our h and k variables come in to change that location. Now, if you'll notice that, a couple of the properties here, we know that there are two asymptotes. And to figure out the second asymptote, of course, I go to 3 pi over 2 or negative pi over 2. And I end up with the same situation where I take negative 1 and I divide it by 0, at which point it's still an infinite solution. So this is why the cycle for one tan cycle lasts pi distance. So from negative pi over 2 to pi over 2, that has a absolute distance of pi, which means that when we go to calculate our transform function, rather than have 2 pi divided by the b, or 2 pi divided by the period to find the b, we have pi divided by the b to find the period. So this is what the tan function looks like. This is the basic tan function without any of the other variables to consider. And this is how we use a unit circle to derive a trig function. And this one is the tan function. So in the next episode, we will explore what happens if you add other variables such as a, b, h, and k. Until then, this is Mr. Tam signing off with another episode, wishing you and your families safety during these times of unease. And I will see all of you in the next episode. Au revoir, arrivederci, bye-bye.